Hi everyone, I am Tze Chien from Malaysia. Currently, I'm working as an exercise physiologist at the National Sport Institute of Malaysia. I'm also studying a master course as an online distance learner at the University of Glasgow. Instead of just showing this poster presentation, I would like to use this pre-recorded session to share more information. So let's get started. The title of this presentation is Blood Lactate and Glucose Measurement in Assessing the Glycolytic Contribution of Para Swimmers During Competitions. Swimming performance is determined by the interaction of multiple energy systems, primarily the ATP-PC, glycolytic, and oxidative pathway. In short to middle distance swimming, particularly between 50 and 400 meters, glycolysis play a dominant role in energy provisions. Rely heavily on the peak power of anaerobic glycolysis up around 30 seconds, while demanding a high contribution from aerobic glycolysis to maintain speed over several minutes. Just to recap, anaerobic glycolysis is the fast pathway to produce ATP. When oxygen demand exceeds supply, the body can't wait for the mitochondria to catch up. Pyruvate is converted to lactate, allowing for rapid ATP regeneration. As shown in this Cori cycle, the liver takes up the lactate and convert it back to glucose. But this process is energy intensive, costing 6 ATP. Therefore, it is an energetically unstable process over the time. Meanwhile, aerobic glycolysis is the sustained pathway in which glucose is broken down more slowly by feeding into the oxidative Krebs cycle. While slower than the anaerobic path, it produces significantly more ATP per molecule of glucose. While monitoring blood lactate is standard practice in sporting setting, the literature on how blood glucose responds during actual competition in para swimming is limited. This is where blood glucose measurements become fascinating. Hyperglycemia during intense exercise or competitive swimming can sometimes be observed and often indicates that the liver is aggressively producing and releasing glucose into the bloodstream to keep up with the high energy demand of working muscles. Therefore, by measuring both lactate and glucose, we can get a more complete picture of these energy mobilizations. This retrospective study aimed to close that gap by investigating differences in glycolytic contribution across 50 meter to 400 meters para swimming event in a competitive setting. We analyzed 51 races from 9 elite male swimmers across 4 different competitions, including 2 local competitions and 2 international competitions. We collected capillary blood samples specifically from the earlobe to measure peak blood lactate and glucose concentration. These are the devices that I use to collect blood samples. Measuring blood lactate and glucose from the earlobe is a better method as compared to fingertip sampling because it provides a sample that better represents whole body lactate and glucose level. This is particularly critical during sport where the hands are actively engaged, such as swimming, where muscle lactate produced in the arm can pull and create falsely elevated reading at the fingertips. After collecting these values, the values were used to calculate the relative energy contribution of the anaerobic and aerobic glycolytic system using the Swannick model. Now, analyzing this data was tricky because we had multiple races from the same swimmers and not all swimmers competed in every event distance. To handle this mixed and unbalanced data without losing accuracy, we use a linear mix model, LMN. This allows us to treat distance as a fixed effect while accounting for individual swimmers' variability as a random intercept. Models were fitted using restricted maximum likelihood estimation. All analyses were performed using the SPSS version 29. Significance was set at alpha less than 0.05. Interestingly, the LMN revealed no statistically significant effect of distance on any of our glycolytic parameters. If you look at the descriptive statistic, you see a trend. The 200-meter event produced the highest mean lactate at 13.7 millimole per liter, which align with the high glycolytic demand of middle distance swimming. The present finding also shows that the glycolytic metabolism is the dominant energy pathway in short and middle distance para-swimming races. Although the p-value were above 0.05, this is likely due to our limited sample size rather than a lack of true physiological change across distances. In summary, while race distance did not show a significant statistical difference in this group, the physiological reliance on both anaerobic and aerobic glycolysis across all distances is undeniable. Measuring both lactate and glucose allow us to see full pictures of para-swimming energy system demand. For coaches, understanding this specific contribution can help tailor training intensity to better match the metabolic demand of specific competition events. That's all. These are my references. Thank you.